All right, so hi everybody. All right, so let's start. So the first presentation will be given by Junyao Peng from Princeton on asymptotics of stability thresholds. So please go ahead.
Okay, thank you. So first, I would like to thank the organizers for inviting me to speak here. So today, I'm going to, throughout this talk, always going to assume that X is a n-dimensional projective KLT variety over C, and L is a big line bundle on X. So first, I would like to introduce the two stability thresholds, the alpha invariance and the delta invariance. So the alpha invariant of L is defined as the infimum of A of V over T of V, where V runs through all divisorial valuations on X. So the A of V is just a log discrepancy of V, and T of V is given by the supremum of V of D, where D is an effective divisor Q linearly equivalent to L. So the alpha invariance has quantized versions called alpha M invariants. So they're defined using similar ways, except that we replace the T invariant by the Tm invariant. And the Tm invariant of V is given by the supremum of V of D, where instead of taking all D Q linearly equivalent to L, you take those D's such that MD is linearly equivalent to ML. So in other words, you only take those divisors coming from the linear system ML. So so I forgot to say that the alpha invariant was first introduced by Tian to study the Kähler-Einstein problem in the complex analytic setting. And this definition I wrote here was essentially due to Demae. And a closely related invariant is called the delta invariant, which was introduced by Fujita Odaka. And nowadays, people all know that the delta invariant characterizes K stability by the Fujita-Lee evaluative criterion. So the delta invariant is again defined as the infimum of A over S, where A is again the log discrepancy, and the S invariant. So one should think of it as some expected vanishing order of B. So to define this S invariant properly, let me first introduce the quantized versions, delta M of L. So again, this is defined as the infimum of the quantities AV over SM of V, where the SM of V is the supremum of V of D, where now I take D to be the so-called M basis type divisor. So in other words, so what is an M basis type divisor? You take a basis as I, where I is from 1 to an M of, so this is a basis of H0 of ML. So this NM is just the dimension of the linear system. And then you take D to be the average of all of these basis elements. Right, so this is the definition of Sm and delta M. And so then you can just define S of V to be the limit as m goes to infinity of the Sm of V. So this one can show that this limit always exists, and so you can define this delta in this way. So a quick remark is that from this definition, one can see that alpha is just the limit of alpha m, and delta is just the limit of delta m. Okay, so with this, recently Jin, Rubinstein, and Tian, they proposed the study of the asymptotic behavior of these delta m and alpha m. So they ask, what can we say about asymptotics? So I believe they have two motivations. So the first motivation comes from a conjecture of Tian, which says that for any smooth final variety X, the alpha invariant of minus k is always equal to alpha m of minus k for all sufficiently divisible m. So in other words, this says that the sequence of alpha m should somehow stabilize for sufficiently divisible m. So of course, one cannot expect the same statement to be true in the general setting, but at least one would expect that the difference between alpha and alpha m can be somehow effectively bounded. And the second motivation, I should say that this comes from so-called quantization methods in differential geometry. So roughly speaking, people in differential geometry, they would like to construct Kähler-Einstein metrics on k-polystable final varieties by constructing it as a limit of so-called balanced metrics of level m as m goes to infinity. And the existence of these balanced metrics of a level m, they're precisely characterized by the condition that these delta m invariants are greater or equal to 1. And so somehow the error term delta m minus delta, it reflects how close these balanced metrics are to an actual Kähler-Einstein metric. So these are the motivations, and let me state the main theorems in their work. So assume that alpha L respectively delta is computed by some divisor evaluation. In other words, just saying that the inf in the definition is actually a minimum and it's minimized by a divisor evaluation. Then the error term bounds alpha m minus alpha is O of 1 over m to the power of 1 over n, where n is the dimension of x, and delta m minus delta is bounded by O of 1 over m. I should also remark that Bloom and Janssen showed that a better bound for alpha can be obtained when L is ample. This is actually O of 1 over m for ample L. So, okay, before stating the main result for today, let me comment on this assumption that this alpha or delta is computed by a divisor evaluation. So this assumption holds in many important cases, including the one where x is a k unstable final variety, L is minus kx. In this case, one can show that, Liu Xu and Zhuang showed that the delta invariant of minus k is always computed by a divisor evaluation. But this assumption is not always true, at least in the pair case, in the log pair case. So this is an example constructed by Aman and Zhuang, saying that the delta invariant might not be computed by any divisor evaluation. Oops. So the main theorem I would like to talk today is it's basically an unconditional version of the above statements. So without any assumptions, we can show that alpha m minus alpha is always bounded by 1 over m, and so is delta m minus delta. Let me also remark that these bounds are optimal in the general setting.
So there's no nth root of M here?
Yeah, there is no nth root of M. Any other questions before I go into the main ingredients of the proof of this theorem? Okay, so let me talk about two ingredients in the proof of this theorem. So the first ingredient, so let me state as the following theorem. So delta L is always computed by a quasi-monomial valuation. For any big line bundle on KLT projective varieties. So this, in particular, this generalizes a result by Bloom and Janssen where they showed, generalizes the result when L is ample. So in the, I guess, yeah. So they basically prove the same thing, but for ample L. Maybe I should quickly define what these quasi-monomial valuations are. So a quasi-monomial valuation of V on X. Well, so this is, in short word, is just a monomial valuation on some resolution of X. In other words, for some weight vector alpha and some local coordinates y1 through yn on y, v of a rational function f. So we can always expand this function as a Laurent series. Then this is just given by the minimum of the pairings between alpha and beta as beta ranges through all the indices where C beta is not 0. So this is just a quick definition of quasi-monomial valuations. And somehow you can view these quasi-monomial valuations as limits of divisorial valuations. So this is the first ingredient, and as you can see, with this ingredient, in order to estimate the error term delta m minus delta, we just need to estimate the error between the SM invariant of this quasi-monomial minimizer V and the S invariant of this valuation B. And so this is done by the second ingredient, which is the Newton-O'Konkal body. With respect to quasi-monomial valuations. So let me also state as the following theorem. So again, V is a quasi-monomial valuation on X of rank R. So this just means that the rank of the value group of V is R. And so usually, again, we assume L is big, then there exists a convex body, delta, in R to the n, such that the following holds. So first of all, so this just follows from the definition of the rank. So there exists a resolution y to x such that this valuation V has weight alpha of the form alpha 1, alpha r, and the rest of the weights are all equal to 0. And these alpha 1 through alpha r, they are Q linearly independent. And the second property is that for any divisor in the linear system ML, suppose I can write mu pullback of D is cut out by a function of the form f equals y1 beta 1 to yr to the beta r plus some higher order terms with respect to v, then this D corresponds to the following a point in the Okonkov body such that the first R coordinate of P are just 1 over m beta 1 through 1 over m beta r. So this sort of tells you how this Okonkov body are constructed by these sections of linear system of L. And the third one is the volume equality, which states that the Euclidean volume of the Okonkov body is 1 over n factorial times the volume of L as a line bundle. So the fourth property, so this last property essentially follows from the first three, but I just wanted to explicitly state it because this is actually the property that we wanted. So it tells you that you can read off this as invariant of V just by the Okonkov body. So more precisely, it's given by the following formula. So you integrate on this Okonkov body of the following linear function: alpha I pi dp. And it is exactly this integration formula that allows us to use convex geometry methods to estimate the difference between the SM invariant and the S invariant, and hence gives you this this bound between delta M and delta using certain convex geometry techniques that appeared in Jean Rubinstein and Tian's paper. Okay, so I think that's all I would like to talk about for today. So thanks for the attention.
Thank you so much. Any questions?
Can I ask a quick question?
Yeah.
So is it important that you get that this function V has a transform on the Okonkov body, right? Which normally is a concave thing, and here is a linear.
Yes.
Do you just use the linearity, or is it important that it's somehow this specific form and these coordinates?
I think I just used the linearity.
Okay.
Yeah. I think this part is quite flexible, and I just want to have some convex body so that somehow I can use the integral points in these convex bodies to estimate the SM functions.
Okay. No, thanks.
Yeah.
Other questions? Okay, so if not,